Hi, welcome to video 36. Video 36 is the first on the ASCII and Unicode playlist, guys. It's video number 1. This video is specifically looking at representing characters as ASCII codes. So the purpose of this video is to understand how characters are represented as binary digits in a computer, to revisit the importance of data types in programming, specifically comparing strings or characters versus number types, to understand the benefits of ordered sequences of binary codes to represent characters, which is what ASCII does, and to briefly mention Unicode as well, so that you are aware that this system exists. As usual, guys, the Python Monster resources on Schoology are there for you to use to supplement your learning in the classroom. You have the videos, of course, you have the booklets, some other useful resources as well, and you've got the 2 catalogue views of the videos, one in playlist categorization and the other one giving you a bit more detail about the videos in sequence as you would find them on the relevant YouTube page. So do use those, guys, if you feel that they would be useful and help you determining which video and resource you want to use. Okay, so as you know, guys, if you've been through videos in the past, you will know that I always like to do a little bit of theory if it's relevant as well, to put the coding into context, but normally that's a precursor to moving on and doing some Python demos quite quickly. It just so happens that when it comes to ASCII on your course, there's quite a bit more for you to be aware of and to know for your exams than with perhaps some of the other hands-on programming topics like if statements or iteration, that type of thing. So let's go through these very briefly, guys. On the left-hand side, all right, characters. You need to know about the use of binary codes to represent characters, the term character set, the relationship between number of bits per character and a character set, and the formats or schemes that can be used to represent characters such as ASCII and Unicode. More on that later, of course. You are required to know, guys, and to be able to articulate in an exam how characters are represented in binary, how the number of characters stored is limited by the bits available, the difference between and the impact of each character set, to understand how character sets are logically ordered, e.g. the code for B will be one more than the code for A. And binary representation of ASCII in your exam will use 8 bits. If that sounds a bit scary, like there's something else that could be a possibility, don't worry, I will cover that off a little bit later in this video. Also, guys, to be aware of the syntax for using Python versus ERL, there's a little bit on there as well. We do use a very, very slightly different syntax in Python than OCR's ERL version, but more on that in the next video, guys, when we will actually be doing some Python demos. Right? I'm just putting all of this up so that you have the full big picture of what's required of you for your exams, and of course exploiting ASCII for your practical programming project, which you may want to do. Again, guys, we'll come on to that when we do Python demos in the next video. Okay, so the next slide I've put up is simply to give you some historical background. You are not, guys, going to be asked to write an essay on the history of ASCII in your exam, but I know a lot of you, myself included, when we study computer science, we do like to have a little bit of relevancy and background. It just brings topics to life a little bit more. So of course, guys, fast forward the video if you don't want to be going through this. I'm not going to talk about it in a great deal of detail, but I will pluck out some important and useful things, I think. The first one is that ASCII stands for the American Standard Code for Information Interchange. Not a surprise then that everybody uses the acronym ASCII, because nobody else can remember the proper name for all of this stuff. It's a character encoding scheme, or a character encoding format. Sometimes you will hear people say, for the ordering of the English alphabet. So that might give you a hint as to some of the limitations already. So guys, historically, we're going back to the 1960s, where the Bell Company over in the States, which was huge at that particular time, was looking for a way to standardize within the context of the first digital computing machines, to have some standard way of representing characters using digital machines. So we're talking here about teleprinters as being the first example of sort of digital computing technology. And I can remember teleprinters, believe it or not, and certainly, guys, it's probably the case that your parents and grandparents will remember the old teleprinters as well. So that's an amusing aside, I guess. So the first edition, the first standard, was developed back in the early 60s and then was updated over time, with possibly the most recent updates being in the 1980s and 1990s, guys. Okay, so at the bottom is probably the most interesting paragraph, I think, because it gives you a sense of the limitations of the original ASCII character encoding scheme, because we only have space for 128 characters. 33 of those are actually non-printing control characters, like the enter key, for example, or hitting the delete key. There are only 94 characters which you would recognize, in other words printable characters, which are used or stored as part of this character encoding scheme. So very limited, guys. Surprisingly though, it wasn't until 2008 that web pages started to move across to a much more flexible format, which is called Unicode encoding, which I will mention a little bit later on, and variations on a theme like UTF-8, for example. So ASCII has been around for a long time, and it was actively used up until fairly recently, 2008-ish. So guys, on the slide you will see one example of millions, literally, on the internet. If you Google images and you simply type in ASCII, you will get millions of these tables, all of them correct, I hope. I've chosen this one because it's really nice, neat and clean, and looks really good in a video because it's nice and sharp. Having said that, it also includes hex and octal number system representations, which I'm not going to cover, guys. Okay, if you're revising, this will be something that's familiar with you anyway. Okay, but if you are new to ASCII and new to number systems, please don't worry about the hex and octal equivalents, because I'm not going to be talking about those. The only thing I'm going to be talking, guys, is the decimal, okay, equivalent, which is the dark blue columns. All right, the binary equivalent, okay, which is the green column, and of course the characters themselves, which are the turquoise columns. The rest, guys, I'm not going to cover off, so you can ignore those. All right, so what can we tell by looking at this one slide, guys? How much of the syllabus scope around character encoding can you deduce from looking at this one slide? Well, the first thing I want to go to straight away, because it can get confusing, this is to look at the maximum number, okay, or the last number in the table that represents a character. It's actually the delete control character that's represented by 7 binary digits of 1, okay, so 7 ones, which is the decimal 127. Okay, so the decimal equivalent of 7 ones is 127. There's two things I want to talk about. Firstly, the limitations of the ASCII encoding scheme by virtue of the number of bits that are actually used, and a question you may be asking yourself already, which is, why is it when there's 8 bits in a byte would this scheme only be using 7 of them? Because it just sounds a little bit weird. Well, the bigger picture of the ASCII encoding scheme does actually use a byte. There are 8 bits in a byte, but the first digit in a byte is restricted and used for something else. So the first digit in a byte is not actively used to represent any of the characters. That restricts us to just 7 bits in the byte, which are actively used, all right, as the encoding of a particular character. 7, guys, to the power of 2 gives us 128. That means that there are 128 possible combinations of zeros and ones, given 7 of them maximum. All right, where do we get the 127 from? Well, that's because within our 128 different possible characters that we can represent, we also need to represent 0. So we go from 0 to 127 inclusive, which of course is 128 different characters that we can represent. Okay, now you can tell straight away from looking at the table, guys, how restricted this is. It did a fantastic job in the day, going back to the 1960s, 70s and early 80s, but you can tell from looking at this that there really aren't anything like the different types of characters that we would want to represent, even in something like a Word document, for example, not here in 2020. So the ASCII table, you can tell, looks very antiquated already. It's very basic. Right, so on that subject of characters, let's talk about the character set. All right, I'll give you a formal definition in a minute. All right, so let's look at the character set of the ASCII encoding scheme. Well, first of all, this is something which was hinted at on the slide about the history of ASCII. Our first 32 representations in our table, okay, or digital representations from 0, binary 0, through to 1 followed by 6 zeros, are all reserved for control characters. These are not even characters that are printed in a document. It's not until we actually get to decimal 33 in our table that we actually start to represent what you and I would recognize as I was going to say useful characters. I'm not sure that's fair really, but principal characters, guys, it doesn't actually start, okay, until we get down to position 33 in our table out of 127. So you can see that that's even more restricted as well. We have, of course, guys, within our character set here, all right, we have a representation of typical non-alphanumeric characters. So we've got some there, guys. We've got a few down here. All right, we've got a few more over here. Okay, and we've got a couple more here. I'm bound to miss some, aren't I? We've got some here as well, guys. Okay, the rest of the character set includes, of course, a representation of uppercase alpha characters from A to Z. Also, naturally, we have the same but lowercase. So we have part of our ASCII table which is reserved for lowercase alphabet characters as well. All of these together, everything that I've mentioned, guys, including control characters, is part of the ASCII scheme character set. All right. So what about a formal definition of a character set? A character set is all of the characters that are recognized by your computer. It's as simple as that. Okay. Now, obviously, if your computer here in 2020 was using the ASCII encoding scheme as a way of representing and working with characters, you would be restricted to 128, which means basically we would all be writing some very, very simple documents and probably doing some very simple maths on our computers as well. More on that later when I talk about Unicode. All right, so a character set is the characters that your computer recognizes, okay, by virtue of the encoding scheme that your computer is using. Clearly, guys, you can tell straight away that in this day and age your computer doesn't use ASCII as its encoding scheme, all right, because we're limited to so few characters and numbers as well. Did I mention numeric representation? I'm not sure I did, guys. I told you I'd miss something there. So obviously the characters 0 to 9 are represented in the table as alpha representations of numbers. Okay, so they would be the character or the string data type when we come to use these in a Python program. Okay, so all of those boxes, guys, represents the full character set available to a computer that uses the ASCII encoding scheme. Right, what else can we deduce from looking at this table? Well, the scope of the syllabus that I mentioned earlier on in the video talked about the sequence. Okay, it said that if you add 1 to A, you sort of get B, and this is a really cool feature of ASCII. So let me get rid of all of these boxes and I'll just show you how this works. All right, if you wanted, all right, to represent the alphabet in sequence, it's of course there, guys. This is the uppercase. Sorry, I haven't got rid of all those boxes. Sorry. There we go. So uppercase alpha characters from A to Z, okay, are naturally in sequence for us. But what's really cool is that by virtue of the way that the ASCII table or the ASCII scheme has been adopted, the binary equivalent, okay, of the characters that represent our alphabet in sequence, and of course also the decimal representation of our alphabet in sequence, are themselves in sequence. So I can go from 65 to 90 in a Python loop, for example, just by incrementing by 1. I can also then use that iteration to print out the alphabet in sequence, okay, because we can actually say that A and plus at 1 gives us B. I mean, it's not mathematically correct, but we can say A plus 1 gives us B simply because the decimal or binary equivalent in the table, okay, there's a difference of 1 between each one. They follow each other sequentially in the table. Likewise, guys, of course, with lowercase, all right, lowercase alphabet is also in sequence, represented by sequential numbers, okay. And if we wanted to write some code where we needed to work with the alpha equivalent of 0 to 9, we can also rely on those string or character sequence. We can rely on those characters being in sequence, guys, because the binary and decimal equivalent in the table is also in sequence. Okay, so that's highlighted the way in which the table has been constructed so that we can access characters in sequence by virtue of the number equivalents being in sequence as well. Good. I think That's covered off the vast majority of things which you need to know, guys. Now, there's one thing I did want to highlight, which was something which goes right the way back to video 1 or your early days in the classroom, where we talked about data types. And we talked about why data types are important. And one of the things I mentioned in the video, if you've seen that video, is the fact that actually your computer needs extra help from you as a Python programmer to put data into context, and we use data types to do exactly that. And if we didn't have data types, we couldn't use a computer programming language correctly. So here's an example of this, guys. Okay, if we look across the row here, this is the one that I actually used in video number 1. I used the @ character as an example, all right, of the importance of using data types in a programming language. All right, so let me just see if I can change the color of my box, because I think this will make it a little bit easier. There we go. Okay, so the actual number 64, okay, in binary is actually 1 followed by 6 zeros. Okay, so if we were doing maths with 64 and we were adding 64 to 1, then your computer would be adding 1 to the binary digit 1 followed by 6 zeros. But we've also said, by virtue of our encoding scheme here, that 64 is the decimal coding value for the character @ okay, or the @ character. All right, so we said earlier, one of the questions we raised was, how does your computer know from 1 minute to the next whether the binary digit 1 followed by 6 zeros is actually being used to represent the @ character in the ASCII table, or whether you're actually wanting to do some maths because it is really the number 64 which you want to add, subtract, divide, take away, or whatever. And there are lots of things which go on behind the system, including the way that the CPU operates and works and all of that type of stuff to help. But one of the things which we need to do to help your computer interpret data correctly and to figure out what to do with the binary code is to use data types in our coding. So the fact that we declare the @ symbol as a character or string data type tells Python that the 1 followed by 60 equivalent is actually being used within an encoding scheme, rather than actually being used as a number 64 to do maths. Okay, so I just wanted, as an aside, guys, to show you once again how important data types are, all right, to help contextualize the meaning of combinations of zeros and ones. Right, guys, okay, one more thing, because it did say right at the beginning of the video in the spec that OCR would be representing ASCII codes using 8 bits. Okay, having completely overcooked the fact that we don't use 8 bits. So how does that work then? So let me put up another slide to tell you what's going on with this strange announcement by OCR of what they're going to do in your exams. Okay, so ASCII codes only use a maximum of 7 binary digits. You know this, guys, already. Okay, here's 7 ones, represents the delete control character. Here's 1 1 followed by 4 zeros and a 1. That's used to represent the lowercase alpha character. Okay, 7 binary digits. But it is the case, guys, actually, that in printed resources particularly, and on the internet, you will find ASCII codes represented by a full byte with 8 digits. And there are a variety of reasons for this. And in fact, if you go onto Google and you do Google ASCII tables, you will often find that a lot of the tables, not this one that I've used, guys, but a lot of the tables you get back do actually have 8 bits in the table. It's just that the first digit never changes. Okay, so here's an example of that. In your OCR computer science exam, you may well see something like this, okay, where the character A, of course, the active digits which are being used, let me change the color, guys, because that's not helpful now, is it really? The active digits that are being used in ASCII, okay, are these ones here. All right, but OCR, amongst other authors, will put an extra 0 on the front, so it looks like a byte, but that 0 never changes, guys. Okay, and again, here we have the 7 ones representing the delete control character, decimal equivalent 127. All right, padded out with a 0 on the front, guys. All right, which is never used. It's just there to make the printing nice and neat. And I'm guessing one of the reasons is possibly to avoid proofreading errors, okay, or printing errors, because somebody thinks there should be an extra character on the front or something similar. Okay, so just because OCR in your exam represents an ASCII character as a byte, guys, please don't forget it's 7 bits that are actively used to represent a character, limiting the number of characters to 128 and no more than that. Okay. Right guys, I think we have covered everything off from the actual scope. The one thing I wanted to talk about was Unicode. Okay, very briefly guys, we will be doing some more in future videos guys, which are optional because you don't need to do them necessarily, but Unicode, I did want to mention Unicode. All right, Unicode is the system by default that's used by Microsoft. The Microsoft operating system uses Unicode. Python uses Unicode. When you see at the bottom of Python and sometimes on the bottom of a document it says UTF-8, which is the coding that's used, okay, that is a variety of Unicode. Unicode stores thousands more characters than ASCII can, okay, and obviously the limitations of ASCII make it unworkable and unusable. So Unicode is used by very many computer systems, and what's really cool actually is that the first 0 to 127 allocated slots in Unicode are the same as they are in ASCII. All right, so we don't have to worry about translating between the two, and certainly in your GCSE, and certainly guys when you do Python code, you don't need to worry about Unicode at all because ASCII is the same. All right, so it's not a problem. Unicode though doesn't use direct sequential representation of binary codes. Now if you look at a Unicode table on the internet, there is some logic behind the code values, all right, but you can't rely on them being sequential. All right, and the reason for that is because an algorithm called the code points is used to encode a character as a binary equivalent. All right, people aren't just simply counting from 0 up to huge binary numbers to store digits, to store characters. Okay, it doesn't quite work like that, and one of the reasons is because complicated character representations like emojis, for example, or the Chinese characters can't simply be represented using bytes or combinations of bytes and bits. So Unicode does things slightly differently. And if you're interested in Unicode guys, I will be using Unicode and exploiting some of that in future Python videos where we do demos. Okay, so that's it for this video. I think we've covered off all the theory. If you're interested in how we can exploit ASCII and Unicode for some fun Python programming guys, join me in the next few videos. I will see you there.